Yalla. About subnets and VLANs. So let's get into there. Have you heard of these topics before? VLANs, virtual LANs, and subnets. Okay, so hopefully by the end of the lesson, you'll say to yourself that you have heard of them. So the key word there is about network segmentation. That is, you take a network and you can segment it or break it into smaller networks. And those smaller networks we'll call subnets. So those subnets can be made to be separate from each other in many ways, which is very useful because having them separate from each other is going to bring these benefits here. It's going to improve performance because each subnet will be its own broadcast domain. The broadcast domain will be smaller. And because the broadcast domain is smaller, you're going to have, well, I was going to say less collisions, but you can do that just with different ports on your switch. But it will be more, your broadcast frames, etc., will go to fewer devices. Maybe one of the key benefits is going to be security, because what you can do is you can separate the subnets so that clients have access to a subnet, but not to other subnets. And so that, for example, in a large organization like we're in here, you could have a subnet for the accounting teachers or the accounting function, and a subnet for the networking function, and a subnet for the teaching function. And that way your teaching people aren't accessing the accounting. That would be good, you know, because maybe we could sort of, you don't want people accessing the accounting, especially you don't want your programming people accessing the accounting, because programming people have the skills to sort of do things that, you know, they could enrich themselves from the accounting program, if you know what I'm saying. So, you know, it'd be enhanced security to only allow access to particular parts of the network to people that require that access because of their job. And yeah, because your network units, your subnets are smaller, so your troubleshooting is going to be easier as well. So if you're given now, we all like our networks, the way that we tend to think of networks and the way that they all seem to work nowadays is we have a network and we have some access to the internet, and we're going to use some cloud tools. So everybody's going to have their access to the internet. They're going to be given an IP address by their internet provider. And so with that IP address, they'll go ahead and connect to their own network, and they'll implement probably a Class C or a Class A or B, depending on how large their organization is. They'll implement their own network, and they'll divide it up according to how they've organized their company, basically. And I hope we'll get that idea here. I mean, the idea is to make your network sort of reflect your own company structure, not just your structure, but particularly the processes that you do in your company, how it works. And so, yeah, and if you've got different locations for different units of your company, that could be part of the way that's working as well. So each, when we have a router, each port on the router could be to a new network. And so that was what we would call a broadcast domain. So we can use our ports on our routers to get to define different broadcast domains, different networks. If we have a big LAN, we can divide that into smaller LANs, and using our router tools, we can actually separate those LANs so that quite significantly, so that the only traffic that's actually going from one subnet to the other is the traffic that we've decided we want to go between them. And so for the reasons, all the reasons that I mentioned above there, you know, to enhance your security, your performance and troubleshooting, etc. Yes. Good question. Yes, we are skipping chapter 7. At the moment, yes. That's Sean's doing that with his class, and I'm doing it with my class. Very good. So here's a scenario, which is a hypothetical. You have a business that's got 20 or 30 computers. They're all in one broadcast domain. And hold on. What's it saying? It's actually grown from having 20 or 30 to having a few hundred. Now, as it grew, it didn't change the actual design. And so it's all in one broadcast domain. One router serves as a default gateway for the entire network. So that's a lot of traffic for one sort of router. So to better manage that network, we want to segment that traffic, so segment that network into multiple subnets. And we find that the company has actually got a building with multiple floors. And so what we want to do is install a router on each floor. And we want to take the IP addresses that we've got and divide them into 3 groups and assign each different group to a subgroup, which is going to be the subnet for that. Now, because we're not looking at particular organizational structure so much, maybe we've assumed that each floor represents a part of the organization, which is self-contained. So maybe floor 1 is accounting, maybe floor 2 is sales, maybe floor 3 is engineering. Maybe it could be something like that. And so at the moment, this is the old or the legacy structure, which is with a single router for the entire company connecting to the internet. And then that router through a single port is connected to switches, which are then connected to each other. Now that's a feasible structure, but it's not a particularly efficient structure. So the suggested structure to get our subnetting going is let's put a router on each floor. And so that instead of having a single broadcast domain, because this is a single broadcast domain. So basically, if we send a broadcast frame from any one of these devices, all of the devices in every floor will receive that broadcast. And so, you know, that's not efficient. A more efficient thing would be to put a router on each floor. And then each of these is a separate broadcast domain. And so any broadcast here is confined to here. So that's, but what it would require is that we isolate for each of those 3 subnets a group of IP addresses which are unique to each of those subnets. Now, because there's routers on each floor, all right, you can think of each of these as a different network, right? That's what routers do. Routers connect different networks, whereas switches connect different devices within the same network. And so the router is making the connections between these. We can still communicate between all of these devices, even though they've been subnetted out. But we can control that communication a lot better. All right. We could say that we could isolate any of these by, you know, making them a virtual LAN and applying some security to them. All right. So I don't know if you've heard this term called a subnet mask. When we do a planning for a network, we want to know how to allocate the IP4 addresses. And we use a subnet mask for that, for IP4. We'll see later in this presentation today that IP version 6, we do this slightly differently. One of the reasons for using one of the reasons that we do subnetting is because IP version 4 doesn't really have enough IP addresses for all of the demand for it. And so, for example, we get a business which is given an IP address by its ISP, its internet service provider. So like Arito gives us an IP address, and then we use a private networking address, a 192.168 address or a 10.10 address. And then we subnet the possible number of nodes that are there or networks from that to meet our particular organizational structure needs. Now, part of that is this concept of a subnet mask. A subnet mask is a way of taking the IP address and putting a mark in it and saying everything to the left is the network part of the address and everything to the right is the node part of the address. We use a subnet mask to make that point. So every IP address has 2 parts. It has a network address part and it has a host address part. And how we decide those is we use our binary sort of number function. So starting on the left, we start with the numbers. We're putting a number 1 in every position. And on the right, we use zeros. And how many ones we've got determines the subnet. Now, you might look at that and say, oh, well, this is actually 255, 255, 255. 255 is actually just 8 ones, okay? If you have a look at that, that's what you're going to get. 8 ones is the number 255. And so basically, if you have a subnet mask of 255, 255, 255, that would be 8 plus 8 plus 8. That's 24 ones separated by 2 dots. That would be the subnet mask 255.255 to 255. If you see a subnet mask of 255, 255, 255, it means that 24 of the 32 available numbers, okay, bits, I guess you could say, in the IP address, because the IP address is made up of 4 octets. 4 octets. An octet is 8 bits, right? And so the bits can be either 0 or 1. So our first octet is all ones. Our second octet is all ones. Our third octet is all ones. And our last octet of our subnet mask is all zeros, meaning the last octet is the octet that we use for determining the nodes. The nodes are going to be the actual host devices. Sorry, I should say use the host devices that are going to be attached to our network. So in a C-class network, we can only have 255 hosts, well, 254 actually, because 2 of the addresses we can't use. But this is how 255, 255, 255.0. This is how it looks, you know, as your binary number, because it's changed to a digital number, right? Sorry, to a digital. Would you? Well, they're all digital. Our base 10. We've changed it from binary to base 10, so we can represent it like this. But this is what it looks in binary form: 8 ones, 8 ones, 8 ones, 8 zeros. That's the subnet mask for a C-class network. Now, you may have seen numbers like this before. Any network that starts with a number between 192 and 200 and I think it's 23 is a C-class address. If it's a 192.168 address, that means it's a private network. And so here's a private network. Using this subnet mask, it means that we're going to use the number 0 to, well, we won't use the number 0 because that's the number of the network, but we use the numbers from 1 to 254 as our hosts on the network. So we could have 254 hosts. Well, maybe that's good, but you know, maybe you want to separate those 254 hosts into some groups. Maybe you want 20 to do this and you want 100 to do that, in which case then you would start subnetting. Yeah, so here's talking, so this is an IP address of a host on this network. The .132 is the actual host part of the address. Everything else is the network part of the address. And we know that from the subnet mask. Subnet mask tells us that the first 3 octets here are the network. So this is our network. So every device on that network is going to have the first 3 octets the same. Only the last octet is going to be different, and that's going to be for their host address. Is any of that familiar to you at all? Yeah, it is. Okay, that's good. All right, so subnet masks. If you have a subnet mask of 255.0.0, so our 4 octets, the first octet is all 255. So that means it's going to be an A-class network. We can see the first 8 bits are all ones. So the network is first octet. The other 3 octets are going to be for hosts. So that gives you a lot of hosts. It's going to be, 254 times 254 times 254. It's going to be millions. I think it's like 16 million or something like that. Now, a B-class network, the first 2 octets are going to be all full of ones. And so that looks like 255, 255, 00. So the last 2 octets is going to be for our number of hosts. The number of hosts is going to be you'll multiply those out. What's that going to be? That's going to be 65,000 or something like that. Now, these numbers here is telling us how many bits are used in the subnet mask. So this is the 8 is referring to these bits here, right? The 16 is referring to these bits here. So 8, if we have an 8, that means it's a network class A, because the first network, and and it's class B because the first are the network. It's class C if the first 24 bits are the network. Now, that brings us to this idea of CIDR, which is a abbreviation for classless interdomain routing. And what CIDR allows us to do is we can take, for example, a C class, a B class, or an A class network, and we can subdivide that network down to have more nets and less hosts in each net. So basically what we do is we borrow bits from the host address and apply them to a network address to give us more networks and less hosts for each network. So every time you add 1 bit to the network address, you multiply the number of networks by 2. Is that 1 bit is going to multiply the number of networks by 2, and you divide the number of hosts that are available for each network by 2 and minus a little bit. But so, for example, this is your standard default for a C class network. This, we know it's a C class because the IP address starts with the number 192. That's in the range for Cs. So this this symbol here with the slash and the number that comes after the slash represents how many ones there are in the network address. So this means there's 24 ones form the network. So that's your standard C class, 3 lots of 8. But if you wanted to have more networks, you could change the 24 to a 25, and that would be dividing the network hosts that you have in 2 to create another 2 networks, and each with less number of hosts. So 24 represents the number of ones in the subnet mask, and so that's known as the CIDR block. Whenever you see an IP address like that, what it means is this machine, the host, the IP address is 127 on that network, and that network, the first 24 bits are the network address, and the last 8 bits are the host address. That's what the 24 means. So what we can do is we can say, well, we only have so many IP addresses. We've got to say we've got a C class address. C class, you've got 256 potential hosts minus 2. You have to say minus 2 because you can't use the first address and you can't use the last address. The first address is actually the network address, and the last address is the broadcast address. But what we could do is we could say, well, I don't want to use 256 host addresses on my network. What I'd like to do is have 2 networks and have each one of those have 128 minus 2, 126 addresses. And so what we do is we increase the number of bits for the network and reduce the number of bits for the hosts. And so we're sort of borrowing. So let's have a look at that. Okay, here's an IP address. And if we borrowed, where is it borrowing the, borrow 1 bit. I don't see the bit being borrowed here. If you borrowed 1 bit, let's say you had this IP address as your network. This is your network address. We know that because it ends with a 0. And so our network has the first 3 octets represent the network address, and the last is our hosts. Now, what we are going to do is, you see the 1 here, the one that they put in the subnet mask. Instead of saying 255, 255, 255, 0, it's saying 255, 255, 255, 128. Where'd the 128 come from? 128 would be the number here. And I hope that makes sense to you, right? This would be number 1, 2, 4. If this was a 1, right? If there was a 1 there instead of a 0, then the 1 at that position would be 1. The 1 at this position would be 2. The 1 at this position would be 4. At this position would be 8. At this position, 16, 32, 64. So a 1 at this position is the number 128. So that's where the 128 comes from, is a 1 in that position is the number 128. So a subnet mask of 255, 255, 255, 128 means that we are using how many bits in our subnet mask? Instead of 24, we've got 25. So this would be represented by a /25. This is a /25 network. So that's how that's represented down there. /25 network means that the first 25 bits represent the network address, and only the last 8 bits represent the, sorry, not 8, only the last 7 bits represent the host address, whatever that may be. And so that is represented by the /25. /25 means that we are using 25 ones. The leading 25 ones represent the network address. All right, so let's look at some others. All right, so all right, this is talking about that same network. Now I mentioned if you have a subnet mask of 255, got this. So we're using this subnet mask, 255, 255, 255, 128. This is our subnet mask that we're talking about here. How that looks is 8 ones. And 7 zeros. That's the same as that. That's how it looks in binary. This is the number. This is a subnet mask. This would be a /25 subnet. Now, a /25 subnet, we've got 20. So we've got seven zeros. So 2 to the 7. 2 to the 7 is how many? Well, 2 to the 7 is 128, right? So we got 128 addresses that we can use for our network, but we're going to have 2 networks. If we took our previous network that had 256 addresses, we divided that by 2 by adding a 1 here. I know. Try and follow me. So we got 128 and 102 new networks, each with 128 IP addresses. Now the problem is the first IP address, we can't use it because it's a network address. So that would be, all right, so it's not actually shown here now. This address here shows us the first address that we can use for a host. First address, we can't use the number 0. We can only use the number 1. And the last address we can use for a host is 126. And why is that? Because the number 0 is going to be our net address, and the number 127 is going to be our broadcast address. So we have to have the last IP address in every network is going to be the broadcast address. And so only available. Look here. Then our next network address is going to be 128. See, we skipped 128. We skipped 128. What happened to 127 and 128? 127 is a network address. So 129 could be a host address, and then the last host address would be 254, because 255 would be a broadcast address. And so if you add those things together, you'd see that instead of, we got 126 plus 126 addresses that are available. That's 252. When we had a single network, we had 254 addresses available. Now we've only got 252. So we lost 2 because we created a new network. two networks here. This is network 1, network 2, out of where we started off with one network. Now we've got 2. Each of them has smaller number of hosts in them. So when we do subnetting, we get more networks and we get fewer hosts in each network. I hope that's making some sense. I mean, I think you kind of have to do it to get used to it. We use subnetting with A, B, and C class networks. All of those can be subnetted. And if we look at the next couple of slides, we'll see how that subnetting affects the number of networks and the number of hosts per network. So each of these, hopefully you know what that means now, right? Hopefully I've explained that so you know what it means. /17 means that the first 17 bits, there's 32 bits in an IP4 address, right? There's 32 bits made up of 4 lots of 8 bits, or 4 octets. The first 17 bits are all for network here, right? And that's the first 8, and then the next one. The next one is going to be 128, right? And then a /18 would be the first 18 bits. So that's why it's 192. 192, where's that number? Is it a magic number? Well, it is kind of. 192 is equal to 128 plus 64. If you add those together, you get 192. What are those numbers? They're the first 2 numbers in an octet. One more, right? So if this is the number 128, and this is the number 64. Add them together, you get 192. So this number is not a mistake, right? It's exactly what we expect. The /19 is going to be add another number there, right? And then you're 32. So that's going to be what? 224. 224. So the 224, that means that the first 19 ones are the network address. And our host address is this stuff out here. So that's what that's meaning. So 20, that's why it's 40, is because you'd add 16 to it, right? We see that the amount that we're adding every time is getting half, right? So started out, we added 128, first one, 64, 32, then 16, then only had to add 8, then only had to add 4. And we're kind of running out of space here when we get down to adding 2. Now the /24, that's a proper C class address. That's the first 3 octets. The first 24 ones are all the network address. But if we're doing this as a what is this? This is a B class network that we're subnetting. You can subnet a B class network. Yeah, so let's look at how it affects the networks and the hosts. So you're giving a network with you started out with a subnet mask of 255.255.0.0, and then you decided to subnet it to go /17. That would be adding an extra 1 here, right? And then you get 2 networks out of the 1 network that you had. You get 2 networks. And each of those networks has half of 65,000 whatever in it. So every time we subnet, every time we move one more byte, we half the number of hosts, and we double the number of networks. Approximately half the number of hosts, but exactly double the number of networks. So when we move to get an extra 1 in our network, we went from 2 to 4 networks, etc. 2 to 8 networks, 2 to 16, and so we can get quite a lot of networks out of that 1 IP address, to the point where, but each one of them has fewer hosts. Now, do you notice these numbers? 32 is not, 30 is not quite 32, right? 60 is not quite 64. 126 is not quite 128. And that's because of the IP address that's required for the network, for the router, and the IP address which is required as a broadcast address. And so every time you have a network, you need to reserve one of the IP addresses for the network, and you have to, for the router port, and you need to reserve one of the IP addresses as a broadcast address. And so that's why you don't get the full 32. or you don't get the full 128, etc. I hope that's explained in a way that's understandable. All right, so that was B class addressing. C class addressing. This is kind of the more common that we do. We typically get in a small network of a business, you're going to get an IP address, which is going to be a C class address. And then you might want to divide up that into something more usable for you. So a C class address is going to give you 256 host addresses that you can use minus 2. 256 minus 2 because of the reason that I just explained. I hope I explained it so you understood, which is that you need to take 2 of those addresses and give them away. One for the broadcast address, and one for the network address. So if you say, oh, I've got the C class address, I'd like to break it up into some more networks. All right, so how many more networks? I want to have 2 networks. Okay, so a C class address is by default /24. First 3 octets, each one with 8 ones in it, right? 8 times 3 is 24. So I got my subnet mask is 255, 255, 255, and I want to divide that into 2 networks. Well, I'll go to /25. That's one more than the /24. I'll be able to get 2 networks. Each of those networks will have 126 hosts in it. Why? Because 128 minus 2 for the reason that I just explained, I hope. Yep. And then, oh, well, actually, I don't want to have 2 networks. I actually need 4 networks. Oh, okay. Well, 4 networks, you're going to have to take 2 bits away from the host. You're going to have to take the 128-bit, and you're going to have to take the 64-bit. And so you'll do that, and that'll be /22. The 128-bit plus the 64-bit, that's going to be 192 in your network mask, right? 192 is 128 plus 64. You know, these numbers recur all the time. You know, they're not just random. No, I need 8 networks. All right. Okay. So you need 8 networks. 8 networks is 2 to the 3. You're going to require 3 bits from the hosts. And so that's going to be 128 plus 64 plus 32. That's going to be 224. That's going to be your network mask now. Your network mask is going to be 27 ones altogether, right? 8, 16, 24, and 3. 224 is what you get with the first three ones out of an octet. So I hope that makes sense. We could keep on. We could go right down to /30. That would give us 64 networks. That's a lot of subdivision, but each network would only have 2 usable addresses in it. So I don't know how practical that would be. You're probably going to end up subnetting around, you know, depending on the size of the groups that you want to have in your networks will depend how you net a network that you're given. If you're given a network with a C-class network, 256 hosts, and you've got 200 people, yeah, you can divide that pretty nicely between them according to the way they're organized, probably. Okay, so in the exam that you might have now, when it refers to exams here, it's not talking about CNAQ exams. It's talking about exams from CCNA. So it's talking about Cisco exams, right? But maybe our CNAQ exams could be like this as well. But definitely, you may decide that networking is the business that you want to be in. You want to be a network person. So you might go ahead after you're finished your diploma degree and you decide to do some Cisco certifications. And you might find that those certifications are not hard to do because a lot of the stuff we've already covered in the courses. Hope. But you would be given questions like this. You're told how many hosts or how many subnets you need, and you're given a network, and you have to create the subnets for it. So it's just basically mathematics. How many networks do I need from this big network? How many hosts in each network? From that, I can see how I'm going to subnet. Given an IP address plus the / value, you might be asked to say what is the first usable host address and what is the last usable host address. Now, I tried to point that out in the previous slides. You know, you can't use the first address and the last address in a network because the first address network address. The last address was the broadcast address. So you would know what those addresses were once you start doing your subnetting. All right, so this is the same network that we talked about at the start of this lesson. And what's happened is they've assigned some addresses to it. So I want to look at these addresses really closely and see if that can make some sense to you. Okay, so we've taken this, it looks like it's a C class network, and it looks like we've subnetted it. What does it say? Do we have a slash value there? Oh, well, we can tell by looking at it, right? We can tell by looking at it. How we can tell is, look, this network, the first usable, oh, there it is, it's /27. So /27 means that we've taken the first 3 bits from the host address to use those as a net address. So that would be, the mask, it's going to be that 255, 255, 255, 224. That's going to be our subnet mask. Our networks are going to be, there's going to be how many networks? So if we did it only one bit, that would give us 2 networks. 2 bits gives us 4 networks. 3 bits gives us 8 networks. So there's 8 possible networks in this subnetting. We know that because of that. And also we could verify that by looking at the network numbers, right? So the first network address in this network is 1. The first network address in this network is 32. So each subnet has a possibility of 30 network addresses, right? Sorry, host addresses, 30 host addresses. So so what's the question, right? So the first network address here is 65. What would be the next? There's 5 other potential networks here, right? There's 5 other potential subnets here. The next one would be, we'll add 32 each time, right? So the next one would be 93. Then the next one would be, etc. Until you got to the last one would be 225. The last network always is the one that has the same number as the subnet address. Yeah, I hope that makes some sense. So each of these networks has a possible 30 computers on it, hosts, because that's 32 minus the 2 addresses that we can't use. Okay, so let's. All right, so is this is also /27, I guess. It says it, well, we can tell just by looking at the numbers, right? So 167 is the biggest, smallest, 172 is the biggest. That's not really telling us a lot though, is it? I mean, right, this network's got 131, this one's got there's 64 difference between them. This one, but oh yeah, what's the difference between, oh, hold on, here's our network addresses, 96, 128. The difference there is 32. All right, 32, yes. So this is the networks, 32, 64. We seem to be, what's the next one? It should be a 90, yeah, 96. 32, 64, 96, 128, 160. And it could be, we could have another one, right? We could have a 192 and we could have a 224. So there's two networks that we could have that are missing. So this one has been subnetted into 8 possible networks we could use. We're only using 6 of them. So there's 2 unused networks here. I hope this makes sense. So this one would be a /27 as well. You can just tell by the network numbers, right? 32, they're incrementing by values of 32. So 32 is, yeah, from your, when you work out the number of addresses, 32 is what you're going to get if you take your 256 possible addresses and divide it by the number of networks. So we know it's 8 networks because 1, 2, 3, is 2 to the power of 3 is equal to 8. And so we used 3 bits. And so that's 8 networks. So that's each network has 32 addresses, 2 of which we can't use. I hope that makes sense. Okay, so the rest of this is just talking a little bit more about the engineering rather than the subnetting. I guess we're going to have to do some subnetting examples. It's really, really fun. But we'll get into that sort of later. It's a little mathematical, but it's mathematical that anybody can do. It's not really tricky at all. So I hope you all kind of look forward to that. So when I say it's mathematical that anybody can do, you know, it's dividing by even numbers, right? Dividing by 2, dividing by 8, you know, dividing by 32. There's no serious math in it, right? And raising to the powers, 2 to the power of 8 is the biggest that we do. So it's not hard. You'll enjoy it. Now, so here's just talking about the technology that you're going to get from your vendor that's going to help you with your building of your networks. So one thing you might want to do is you might want to have a DHCP server, which is going to provide you with your network addresses. So that's good. So people just plug in or connect through the Wi-Fi or whatever, and they're given an IP address. Well, what if you separated your network into, you know, you've subnetted, you've got a single network and you subnetted into 3 different networks? Are you going to have 3 different DHCP servers? That's kind of a lot of money and a lot of hassling around. So our technology is a little bit better than that. Even though we've separated these networks out, we can have a DHCP server on one of the connected to one of the routers, and the others can sort of kind of VLAN into it. They can sort of tunnel into it and get their IP addresses with, even though they are technically in a different network because they're separated by routers. So that's the idea there, is you can have a layer 3 switch or a router which is using this this technology so that your DHCP assignments can go from you can manage them on your network even though you've subnetted your network. That's the idea of that. So you can have this thing called a relay agent that makes that possible. Now this idea here is really cool. The problem is not enough IP4 addresses. That's the problem. One solution is, well, we'll just use IP version 6. But, you know, a lot of people still aren't using IP version 6. So if we're going to stay in it seems that we've stayed in the IP version 4 world for a long time, and maybe we're going to be here for a little bit longer. So IP version 4, how do we sort of fix that problem? Subnetting is part of the answer. Now, we can divide it every time, dividing by half. That's one thing. So we could end up with 64 networks or something like that. But what if you've got an uneven distribution in your company? You've got 256 people in your company, or sorry, 250 say, but 120 of them are in one division, and then 30 are in another division, then 17 are in another division. Get the idea? So, I mean, just dividing them up smaller and smaller, you got a big problem because you want to keep 120 of them together. You're going to give those 125 different networks. What if you want them all just to be on one network? And so we have this concept here, which is your variable length subnet mask. And the idea of the variable length subnet mask is that you do one, you divide your network into half, and maybe you can use that. And then the remainder, you can work with the remainders, right? You can say, okay, the remainder will divide that in half and make 2 subnets out of that. And this diagram is sort of representing that. So, you know, half your people were in sales, a quarter of your people were in accounting, 1/8 of your people were in HR, and 1/16 of your people were in each of these areas here. And so we can do that. We can say, okay, we're going to divide it once here. We're going to have different subnets masks for each of them, basically. So we have our variable length subnet masks. And so this is how that is represented, right? So we're using /25 to get our sales subnet. We need 120 hosts for that. /25 will give it. We use /26 to get our accounting. So /26, we're going to have, that's doubling the, we're going to have, when we did the /25, we took our one network and now we got 2. And then we say that one part of the network, that's all gone to sales. So we got this other bit here. Oh, but we're going to divide that in half too. That's what we're saying is we're going to take the remainder, divide it in half, and take some number less than 62. Yeah, 54 works. And that's going to go to accounting. And then the half that's left behind, well, we're going to divide it again. And then, so some number less than 30, 25, it's going to go for HR. And then we're going to divide that again and divide it again, right? And so that's basically what's happening. Now, before we did this, we would have been careful to observe what were the numbers of hosts that were required for each of those little networks. And then by analyzing that and seeing that we needed 120 for sales, and which is almost 126, and 58 for accounting, which is almost 62, and 25, which is almost 30, we were able to determine how we could do our variable length subnet masking. So you know what this means, right? The simple, it's always best to use the simplest explanation possible, I think. /26 means the first 26 bits in a network, in a IP address are the network. /29 means the first 29 bits in an IP address are the network. So that's what it means, as long as we keep in mind what the slash means. And why is that important? Because we divide up every IP address into two parts, the network address part and the host address part. And so this is a way that they've done that variable length subnetting. Actually was able to take a only 256 addresses and get a nice division of it, and actually have sales. The /25 has allowed sales to have 120 addresses in there. Well, they could have had 126, right? They used 120. All right, so the next points there, as I said, the problem is not enough IP addresses. The solution is subnetting for IP version 4. Another solution is just use IP version 6. And so IP version 6 makes it a little bit easier. Your subnetting just requires you to just sort of specify these particular IP addresses will be that subnet, and those particular will be another one. And how we do that is with in the address. So you know your IP version 6 address is a much longer address, right? I think it's 128 characters as opposed to 128 bits instead of 32 bits. And so it's giving many, many more potential addresses. And so what we can do is we set aside, as it says there, the last 4 blocks identify the interface. But what we're going to do is we're going to add into this, into the identification in the IP address, we add a couple of little, we add a block, I guess it's called, or 4 hexadecimal characters. We add in there an identifier which tells us about that network, and show that here, right? We call that our subnet ID. We can add in there, just sort of add to it, the identification of our subnet. And so we don't have to go and do the subnetting with and come up with special IP addresses that are separate from what we started. We just have to reallocate the ones that we've been given already with IP version 6. So it's a little bit easier from that point of view. Then, so you might ask yourself, well, why doesn't everybody just use IP version 6? I don't really have an answer for that, because IP version 6 has been around for at least, I don't know, 10, 15 years. People still aren't all using it. All right, so brings us to this point about VLAN. So this is a new topic. So a new but related. So the idea of VLAN is a virtual LAN. We can use that for security purposes. So we can set up our virtual LANs so that we could have people sitting beside each other, all connected by Ethernet cables to the same switch, but not able to see the same servers, not able to log into the same systems. So we can do that with our virtual LANs. And so that, I hope, is represented by this diagram here. We got these guys sitting beside each other in the same room on building, and building, I don't know, they're in the 3rd floor. But these people here, they're able to use the manufacturing VLAN, and they're not able to see the administrative VLAN, even though the person beside them is. And so these people are logging in differently. And look, they're connected to the same switch and everything. But we do have some control through the router, which is these people are connected to that VLAN and those people are connected to that VLAN, even though physically they're all connected the same way. So why would we use VLANs? I hope that I've made the point that it's very good for security. Here's some other reasons. We can isolate heavy and unpredictable, isolate if we have a part of our network which is using a lot of traffic and it's sort of affecting the performance for everybody else. We can isolate them and say, okay, well, we're going to give preferential sort of access to these people here in this VLAN, and so they're not going to be affected by your use of YouTube or whatever it is that you're streaming that's sort of taking a big toll on our network. You're going to only get this bit. Separating for security, I hope I've made that point. That seems to me to be a very important part of using VLANs, to have the admin people separated from the other people, and particularly to have the accounting people separated. Maybe you've got some protocols working on a particular server that would mess up other things happening somewhere else on the network, so you could isolate them. But the recurring word, the thing that we see coming up and again is we want to isolate different parts of a network from each other. And we do that using VLANs. All right, so the next couple of slides is about that, but talking about how we use switches and routers for that. So we can just use an unmanaged switch. The problem with that is that the control is not there, and we might find that it's not going to sort of work the way we wanted it to. And as it says, there's no IP address assigned. With a managed switch, you're going to assign an IP address actually to the switch, and then you're going to have some control that you're going to have over that IP, switch, not just by applying an IP address, but by the software that you have installed on there. But you're going to need to have that managed switch if you're going to use a VLAN. So your unmanaged switch is not going to work with VLANs. And so you're going to be able to assign the ports using software on your switch. You're going to be able to assign the ports to work for different VLANs. And I think we got some diagrams on that. Yeah, so this diagram here shows that. So it's showing that this particular port here is going to be assigned to VLAN number 2. These 2 ports are assigned to a different VLAN, this one again to another one, and these 3 ports for another one there. So that's quite possible to do. And they don't even have to be contiguous. I think we've got a diagram that sort of shows that as well. So how does a normal switch work? It forms a connection between the router and the LAN. Yeah, okay. And how does a VLAN switch work? So with the VLAN switch, a particular port is going to work for a particular part, a particular separated LAN. So that's our virtual LAN. The switch is being used to segregate the LAN. So you're going to have software on that switch that makes that possible. And the software is quite powerful, which is shown by this diagram. The color coding there is showing that all the blue stuff represents ports that are assigned to the VLAN 1, and all the red stuff is ports that are assigned to VLAN 2. So we're able to do that assignment. Each of those ports could be assigned to whatever VLAN we wanted, I guess. That you can see that they don't have to be contiguous. It doesn't have to be one big block, which is VLAN 1, and one big block, which is VLAN 2. It can be anywhere, any way we just want to assign those ports we're doing that. And so that kind of gives us the V in VLAN, I guess. V for virtual LAN. And so, yeah, it's all basically done by software. All right, so we have this term called 802.q1.q, and that allows us to sort of work with making that assignment. You'll see that this becomes an insertion into the frame, which is going to identify a particular frame to a particular VLAN. So in other words, what we're saying is each VLAN is going to have its own kind of frame. The frame is going to identify that that traffic belongs to that VLAN. And so it can go through the same switch, and the switch is going to be able to I don't want to use the word route because that sounds like router, but it is kind of like that. I guess it's going to be able to transfer that frame to go to the right, to the correct VLAN that it belongs to, and not to the ones that it doesn't. So it adds a new tag, which is this 802.1q tag, into the frame, which allows it to make sure that it gets to the right VLAN that it belongs to. So you can see that happening here. In the frame, we have extra 4 bytes that are added, and this is sort of VLAN technology, adding that extra little bit of information, which is basically identifying that this particular frame belongs to a particular VLAN. And so because of that, what this diagram is really trying to show you is that even though we've got, look, all of these things are connected to the same switch, but the technology, the software in the switch is able to manipulate the frames by inserting extra information in the headers that will allow the switch to make sure that the VLAN stuff for here, it doesn't get mixed up with the VLAN stuff from there, right? Or from there, right? The guys over here in this that are connected to this switch here, they can be sitting out here connected to that and working with people connected to this other switch. But they won't get crossover with these other people, right? And that's because each of those frames that gets passed through that switch has got that identifier on it that it's only going to go to this port, right? This is the VLAN 1 port, and that's the only way that any of those VLAN frames are going to go. Likewise, the VLAN 3 traffic is only going to go to that port there. It's not going to find its way to these ports in that other switch. I hope that makes sense. So it is a port on the switch is going to be configured. Now here's talking about it's going to be configured to into the network or between switches in the network. So an access port is going to connect to your hosts on your network, whereas your trunk port is going to be used to connect to another switch. And so it can manage traffic in multiple VLANs. We'll see that. So trunking protocols, they work with your VLAN tags, and so are able to manage the frames going between the different switches to, all over the network. And there's a special software that we've got from Cisco, VTB, which is VTP trunking, VLAN trunking protocol, which allows you to sort of, I think the next diagram shows that pretty well, where it allows you to make sure that your frames are going to the right part of your network. Yeah, but the point here is about you can have a you've got these access ports here on this switch, all except for this one purple one are access ports. So you got access ports for one VLAN, are color coded, that's VLAN 1, and VLAN 2 has its other ports, and the trunk port is used to connect to another switch, so that yeah, a different part of the network can be used. Now, this diagram shows that quite nicely, I hope. The trunk ports, so we got trunk ports on each of these switches, and you see them connecting to the other switches and to the router. But okay, so over here on this machine, we have the connecting through the access ports. The access ports are going to connect to the individual hosts. Now, the important thing is these guys here in the blue, they're on a different switch, right? And but they're still part of the same VLAN as these guys here. So though these guys here are on switch B and these guys here on switch A, as far as they're concerned, they're on the same network as these guys, where they might be sitting in the same room with these guys here who are on VLAN 2, but they don't have access to the same servers. You know what I mean? They're not having the same experience as the guys in VLAN 1, but these guys are. And how is that network traffic getting there? This guy can be working with these guys over here. That network traffic is going through that switch over a trunk, right? Through the trunk port, over another trunk to the switch, and then back out another access port. So access ports and trunk ports are important in making those work, right? So the trunk port is actually working for all three of these VLANs. And that's what that means there, right? So VLAN traffic from VLAN 1, 2, and 3 is all going on that trunk port. But these access ports, this access port is only for VLAN 1. This access port is only for VLAN 1. This access port is only for VLAN 2. And this access port is only for VLAN 3. I hope that makes sense. So when you set up and configure your switches, you're going to assign IP addresses to the ports, and you'll do that based on the work that you've done on a pencil paper, you know, doing the subnetting. So the subnetting is kind of a logical exercise that you do to decide which IP addresses to use for which of your network, for the networks that you're creating. And then based on that, you'll go and do configuration of those ports. So we've got our ports here. So that's going to be a trunk port, right? And we will set them up according to how we've organized that subnet. All right, so this is talking about how we set up the VLAN. The first couple of points there about the default VLAN and the native VLAN, they sort of hold sort of dangers for us. Default VLAN, kind of as you'd guess, that means that we haven't actually gone in ourselves and done a lot of configuration. We just accept the configuration that's given to us on the switch. And basically, it's going to include all the ports are going to be available to that. So that's not going to give us our VLAN capability that we want. Native VLAN, if we don't tag our frames, or if we haven't organized to tag all our frames, remember we've got that protocol which puts a tag on the frame mentioning which subnet it belongs to. If we're not doing that, then all of those frames will end up on the VLAN. So these are suboptimal ways of working with our VLANs. So with our data VLAN, management VLAN, we kind of want to, we do want to manage it. And so we want to make sure that we're using our VLAN in the way that we should be. Yeah, so let's have a look. Next slide here. All right. This might be a bit hard to see. You might. Basically, what it's showing is that somebody is going to the console, putting in a command, which is basically to show us what's going on with the VLAN. And they're able to see that this LAN has been subdivided into a bunch of different subnets and VLANs on that. So you do have some control that you can sort of use on your switch to sort of give you sort of reports like that. Some things that could go wrong, or these refer to the previous slide that we were just talking about. Maybe if you didn't sort of specify which ports you wanted to use, you could end up with your default VLAN, and basically your frames could be going anywhere. Yeah. On the other hand, you could isolate a VLAN so that it wasn't able to contact anybody else. The last point there is about VLAN hopping. That I guess you could almost use the word hacking there, I guess. So basically what we're talking about is intrusions that can occur because you haven't set up your VLAN correctly. And so that an attacker can access your VLAN and inject software that's deleterious. So what they could do, for example, is that they could get one of these tags and add it to their frames and sort of trick into getting into your VLAN traffic. And so yeah, so we could do that with double tagging. Switch spoofing. So in this one, it's kind of like the attacker sort of takes over one of the trunk ports. And so then just on the other end of that trunk line, sort of emulating that they're providing the network. And so they're able to divert that VLAN traffic to themselves. So, you know, the standard sort of hacking type ideas sort of follows over from before. So this goes back to that previous slide. Don't use the default VLAN because you don't really have enough control over it. Likewise for the native VLAN, because a native VLAN, if you've got unused VLAN IDs, those things you are not going to be able to control. So likewise with the idea of disabling auto trunking, you want to actually, basically you're going to try and grab as much control of that as you can, and you're going to do that by your configuration of your VLAN. So configure all the ports as access ports, unless they are to be used as trunk ports. Don't leave ports unconfigured. Yeah. Specify specifically, you know, which of each one of those ports, what they're doing, each trunk, so that, as I said, so that it can't be sort of taken over in some way, or so that data can't get sort of leak out. Physical security methods. That's you know that security is always in layers, isn't it? And so physical security is separate, but it's just one more layer that's going to help you. So there's our summary of what we've been talking about. I think the fun part of the lecture and the sort of more practical part from our point of view that we're going to go idea of the CIDR subnetting. And I haven't seen the notes that we're going forward, but I expect that we're going to have a few examples of doing that. That could be a bit fun. You know, as it said there, it sort of highlighted that you might be preparing for exam questions in Cisco, and they would be questions like, you know, you've got a network which is a C-class network, and you know you've got 230 hosts that you need to connect to this network, but the network administrator wants to separate 50 of them into a subnet, or the network administrator wants to create I don't know, 6 subnets from that. How would you do it? And how many hosts would you have on each one? That type of thing. Those are the type of questions that could probably come up. Class A, B, and C can all be subnetted, and VLSM, that allows for a lot of flexibility in our subnetting. So yeah, we saw that. I hope that made sense. IP version 6, it's better. Why aren't we all using IP version 6? I know it's supported by most of the operating systems that you're using in your network operating systems. And yeah. I'm going to stop there. Plus. Anyway, so that was a marathon. And